Hello and welcome to the Car Care Nut channel, and welcome to the beginning of a new series. In today's video, we're going to talk about how electronic fuel injection in modern cars actually works and how did we arrive at what we are at today with super modern direct injection and everything else. This is a two-part series, so this is part one where we're going to talk about most of the stuff. Next part, we'll talk more about the advanced stuff. Let's start with the first question. Where did it actually start and how did we arrive at electronic fuel injection? Right after this. So let us start with the very basics. Every engine needs three things to happen for it to run. Maybe four, let's go with three. You need gasoline, you need air, which has oxygen, and you need an ignition source so we can ignite that mixture. And off we go. It's a lot more complicated than that. If you know the details, I will leave this video right here with how engines actually work. But in order for us to get air into the engine, it's actually very simple. Just by the nature of how engines work, every time the piston comes down, it creates a vacuum that pulls air into the engine. So that happens naturally. But how do we add fuel? And more importantly, the correct amount of fuel so the engine will actually run? We started with cars with carburetors. In case you are not familiar with what carburetors are, they are the most archaic device ever. And that's why we moved away from it. So here's how, very briefly, how carburetors work, just so we can understand how things happen. You have an engine that is 6 cylinders, V6. You have there's a runner for each cylinder where the air is going to go in and the fuel is going to go in, which is already mixed and ready to go. Carburetors, they are single source. So you're going to have fuel go in the middle and kind of hopefully get distributed between all the cylinders, hopefully equally. So carburetors, very simple. They have a passage in the middle, and then you have kind of a restriction in the middle of that passage, and then the passage opens up again. That's called a venturi. And then to the side of that passage, you have a little pipe that goes into a little ball that has a bunch of fuel in it. When air passes by, when you hit that restriction and then it opens back up, it's going to increase the velocity of that air. That creates a pressure differential between the air past the venturi and the air on top of where the fuel bowl is. So higher pressure here, lower pressure here is actually going to push that fuel into the passage, and off we go. The more air you let in, the more of that effect will happen, the more fuel will be kind of pulled into the mix. So when you press the gas in a carbureted car, there's a throttle plate that will open, allowing more air or less air to come in, and that will correlate to more fuel or less fuel. In addition to that, and this is important that we understand it because it's relevant to what we'll talk about, carburetors have a small pump that every time you push it's a mechanical pump. Every time you press the gas pedal when the car is off, it's going to spray a little bit of fuel into the intake. That's just to help the car start. That's why, if you remember in the olden days, you had to pump the gas a few times for it to start, because you need a little bit of fuel to go in. As long as the little container of fuel is full in the carburetor, that will happen. That sounds like a disaster waiting to happen, if you ask me. Something had to change, and this is when the revolution of electronic fuel injection started. So we start with the modern times, but to start with modern times, we got to go to the history a little bit to understand. Actually, the early versions of the attempt of electronic fuel injection started in the 50s, never took off because of the limitations of the computers at the time. Until the 80s, things really went into high gears. That's when emission requirements came about, where you can't have this just giant random occurrence of a carburetor do proper emissions. And then computers became very advanced, where now you can have a small computer inside of a car to run the system. So the early versions of electronic fuel injection started kind of mimicking a carburetor. Just having one injector, spray fuel, the computer controls that, and it basically mimics exactly what the carburetor is doing, but electronically. Instead of letting that Venturi effect pull the fuel, we just have an injector. That was called single port fuel injection. That means you are spraying the fuel and letting kind of the natural suction of the engine pull that fuel and distribute it across all the cylinders. That was basically a glorified carburetor, a very complicated carburetor. That's basically what it was. But then the breakthrough came about when we started with multi-port fuel injection. And that's what we're going to dive in this video. So let's get into it. So here's how multi-port fuel injection, let's start with that word. So there is an injector for each port. Let me translate that. There is an individual injector for every single cylinder. Now we have precise control, how much fuel and where it's going exactly, not just kind of dumping into the mix and hoping for the best. So here is the best part. The fuel injector is actually a very simple device. It is extremely simple, the idea behind it. So you have basically a passage with a small plunger that is controlled by a small electronic solenoid. You apply power to it, that plunger gets pulled by the solenoid up, opening a passage. You shut it off, it just comes down and it closes. That's it. It's a glorified faucet. That's basically what an injector is, in essence. But wait, how are we gonna get the fuel into that injector so it would spray it? Is it just gonna dribble out? Aha. This is where the magic is. So in order for these injectors to actually spray fuel, not dribble it out, because we need a fine mist of fuel so it would vaporize, and that's actually what's going to go inside. Because if you just dump raw liquid fuel into the cylinder, you're going to hydrolock it. That's the problem. So you want to atomize that fuel. You want it to be in vapor state. So it needs to be a very fine mist. Here's how they actually did that. Multi-port fuel injected cars, they have an electronic fuel pump in the tank, in the gas tank, that takes that fuel, sends it to the front at pressure. Then on the injectors themselves, there is a rail, basically a container that sits on top of the injectors connected to all of them. And pressure starts to build up in this rail. So here's what you have. You have the pressure of this rail pushing on the injector, waiting for it to open. So when you now open the injector, it's going to come out with high pressure. When you spray something at high pressure, it's going to tend to kind of fan out. And depending on the design of the tip of the injector, it's going to create that fine mist because now it's under high pressure. Pretty cool, right? So now that we have that pressure sitting in the rail, the computer will very simply open that plunger. It'll spray fuel, shut off the plunger. We stop the plunger. By the plunger, I mean the injector. And the way it does that, the computer, is very simple. You have power and you have ground. You have two wires to every injector. Even in 2024, all modern cars will have two wires to every injector. One of them is power, and usually with car design, they will have that power always there. Then you have a second wire, which is ground, and that's how the computer is going to control it. It's actually going to pulse that injector on the ground. And what it's going to do is, okay, we need to spray fuel. We're going to open that injector a little bit and shut it off. It's sprayed. And it's simple as that. You have that pressure there. You have control over each individual injector. Just open it, close it. We just sprayed. We're good. We figured it out. We got it. Wait a second. How does the computer actually know when to fire each cylinder and which one? This is where advancement in sensors and computers and everything played a big role in figuring this part out. So let's go back to the basics of an engine, because this is very important. We want to spray that fuel when the engine is on the intake stroke. Pistons coming down, pulling the air-fuel mixture down into the cylinder, into the combustion chamber, and the intake valve is open. We want to pull that stuff down. But how does the computer know when that is happening for each cylinder of the engine? Because remember, now we're multi-port. We're spraying for each individual cylinder, not for the whole thing. So here's how it's going to actually do that. The crankshaft position sensor and the camshaft position sensor, these are sensors that give the computer a kind of a 3D image of what's going on with the engine, where it's at any given point. First, the crank position sensor. So the crankshaft position sensor tells the computer how fast the engine is rotating, the RPMs. That's actually where you get your RPM in modern cars. And then when does the cycle start? When did we have a full revolution of the crank and we're starting over? This is very important information. So the computer would know how fast the cycle through all the cylinders firing is going. But that doesn't tell it one thing. See, the piston, when it comes down, it could come down in the intake stroke or the power stroke. When the power stroke happens, we don't want to spray fuel because we're not there yet. We need to spray the fuel around the intake stroke. So how does the computer know that from the crankshaft position sensor? It actually does not know that. It uses another sensor called the camshaft position sensor, because the camshaft is what's gonna determine, are we in the intake stroke or are we in the power stroke? And that's how it's gonna know. So now the computer knows how fast the engine is turning, when does my rotation cycle starts again, and more importantly, which cylinder is at what stroke. That is the vital thing. So every time the cycle starts, okay, cylinder, let's take a hypothetical firing order 1, 2, 3, 4 for simplicity. Cylinder number 1 is at intake stroke. We're going to fire that injector. We're going to power it up, send the fuel in there. Then cylinder number 2, cylinder number 3, the cylinder number 4. And now we see that the crank position sensor hits its kind of reset, or we're back to the beginning of the cycle. Okay, back to the beginning and keep going. That's the cool thing about it. And the coolest thing about it is once the computer picks up the beginning of the cycle, it actually doesn't need the cam position sensors anymore. It uses it for other stuff. But as far as the firing, it already knows. That's the coolest thing about this. So that's it. The cycle is complete. We have figured this out. But wait a second. We know how to get the fuel in the cylinder or in each individual cylinder. We know when to send that fuel, and we know to which cylinder. But how do we know how much? Air-fuel ratio is a term you're going to hear a lot, and it's the most important thing with multi-port electronic fuel injection. If you want to have the perfect combustion of gasoline where you have the complete usage of that entire part of gasoline, you need to maintain the following ratio, 14.7 to 1. Let me explain that. For every gram of fuel to completely combust to its entirety, you need 14.7 grams of air. But wait a second. How is the computer going to know to maintain that perfect ratio, which by the way is called stoichiometric ratio? That's just a fancy word. So how is it going to know how to maintain that? This is where things get really interesting. The engine will pull air. Granted, it's a natural aspirated engine we're talking about here. It's going to pull air naturally when the piston is coming down, the valve's open. It's going to pull air from outside like a pump. So how do we measure how much air the engine is breathing, basically, or pulling in, so we can match it to maintain that 14.7 to 1 air-fuel ratio, so we can have a clean burn and an efficient one? Here's how it's going to do that. Two ways the computer will actually measure the amount of air that is being pulled into the engine. One of them is a very popular one, actually one that is the most commonly used today, mass airflow sensor. The second method is MAP sensor, or manifold absolute pressure. Here's how these two work. Start with the mass airflow. It's the most common one. So there's multiple designs of it. We'll talk about the most common one and it'll give you an idea. So the mass airflow will have two hot wires across from each other. As air passes through them, they will cool down. The computer will measure how much the temperature drops or how much effort it takes to keep that temperature, and it will actually calculate exactly what is the airflow, how much air is going into the engine. That is method number one. MAP sensor is completely different. MAP sensor measures the difference between atmospheric pressure and the pressure inside the intake manifold. It runs it through a little calculation and it determines how much air do we have entering. Now, when the computer knows how much air we are taking in, it's a very simple thing. We're just we have this much grams of air coming in, for example. We're gonna spray this much grams of fuel. We got 14.7 to 1 and things are wonderful. That's it, folks. The cycle is complete. We figured out how to get the fuel in there for each cylinder. We figured out when and which cylinder to fire. We figured out how much fuel to send in. That's it. The engineers, they are getting their trophies. They are retiring. That's the end. But wait a second. How about when the temperature changes and that air that you're bringing in actually is more dense with oxygen or less dense when it's really hot? How about when you have bad fuel, wear and tear, bad filter, all these variables? How do we know that what we're actually doing is actually working? This is the point where computers and the engineers that designed them got really advanced with things. And now, just like a kid at school that thinks they are doing great, but they take a test to find out if they actually did well or not. So this is the test of the computer. This is how the computer tests. Are we doing good at keeping that 14.7 to 1, or are we not? Are the elements changing things on us when we assume things are going well or not? And this is how it does that test. There is a little innocent sensor that sits on the exhaust called the oxygen sensor, or sometimes referred to as an air-fuel ratio sensor. They are not the same, but we are not going to get into complicated details here. That is how the computer runs a test to see, are we maintaining 14.7 to 1 or not? And you might be asking, why is it called an oxygen sensor? What does oxygen have to do with this? Well, see, engines are taking air in, but we actually don't care about the air. We want the oxygen because that's what we use to mix with fuel to ignite. That's the only thing we need. So if we have a perfect mixture, 14.7 to 1, what comes out of the exhaust has no oxygen. We have used all the fuel, all the oxygen available. We have no oxygen. That is the perfect kind of middle ground. But if we have a lean mixture, meaning we have more than 14.7 grams of air to every gram of fuel, we have excessive amount of oxygen. That oxygen is not going to get consumed by the combustion. It's going to come out of the exhaust. So the oxygen sensor is actually going to detect that being an elevated level of oxygen. That's how the computer knows when we're running lean. And on the opposite side, if we have less than 14.7 grams of air and 1 gram of fuel, you're not going to completely combust that 1 gram of fuel. So you're going to completely use up all the oxygen and you still have fuel. Well, the oxygen sensor is going to notice that there is 0 oxygen or complete lack of oxygen. That's how it's going to know. So the computer is going to use this input to determine, are we running too lean or are we running too rich? So we can make micro adjustments so we can keep that 14.7 to 1 going, even with variables that are uncontrollable. You can't just set it and forget it. Things will vary as you go. That's how it uses that sensor to actually figure that out. And the way it's going to make those adjustments is very simple. You can't change the amount of air that is coming in. You can't restrict it or change it. That's not viable. The way it's going to do that, if my mixture is lean, meaning I have a lot of air, very little fuel, I need to put more fuel, I can't control the air, we're going to increase something called injector pulse duration. Basically, remember that plunger that I told you the computer opens with a solenoid? We're going to open it a little bit longer, period. So we're going to spray more fuel to equalize things and keep it going. But if we're running too rich, meaning we have too little air coming in and too much fuel, we're just going to decrease that duration. Open that injector a little bit less, have it spray a little bit less fuel. We are good. Folks, they got it figured out. That's it. Now they have completely earned their retirement. They have got the trophies and the awards. That's it. They figured everything out. But wait a second. What about when you go overdue on your spark plugs and your air filter is dirty and you are really driving the car hard and all of a sudden you're not driving it hard? What about wear and tear when that engine doesn't have as good of a compression anymore, and then you're driving through this city and driving through that city and temperatures and everything is changing? How is it gonna know What's going on with everything? Is it just going to keep chasing after the O2 sensor all day long? And that question is what's going to take us to part 2 of this series. That's when we're going to talk about more advanced things. We talked about the basics now. We figured out the problems as they come. The advanced things are, how is the computer going to accurately monitor if we have variations or we have a problem? And this is very important. Folks, I hope this was not a lot. I tried to keep it as simple as possible for us to understand and kind of just enjoy how beautiful the technology of electronic fuel injection. But in the next part of this series, things will get serious. So stay tuned. That part's coming very soon on the channel. I hope you find this video helpful and informative. I hope you learned something new. If you like it, consider giving it a thumbs up. If you're not a subscriber, consider subscribing to the channel. Until part 2 of this series, may the Lord bless you and keep you, and you have yourself a wonderful day.